Welcome back to G Fun Facts Online. Today we are stripping away the silence of the vacuum of space to listen to the secret song of the solar system's innermost planet. When we look at Mercury, we usually see a silent, sun-baked rock, a cratered world that seems geologically dead and frozen in time. But if you could trade your eyes for radio antennas and tune in to the electromagnetic frequencies swirling around the planet, you would not hear silence, you would hear a song. It is a strange alien chorus of rising chirps, whistles, and sudden squawks, sounding eerily like a flock of birds waking up at dawn in a dense forest. This phenomenon is known as the Hermean Chorus. It is a symphony of plasma waves that reveals Mercury is not a dead world, but a highly dynamic, intense, and physically bizarre environment. Over the next 20 minutes, we are going to deconstruct this invisible symphony, explore the physics of how a planet sings, and understand why this discovery by the BepiColombo mission changes everything we thought we knew about the closest planet to the Sun. To really appreciate this, we have to look at how our understanding of Mercury has shifted. For decades, the consensus was that Mercury was magnetically boring. In the 1970s, the Mariner 10 spacecraft surprised everyone by detecting a magnetic field, but it was weak, about 1% the strength of Earth's. The assumption was that this was just a miniature, feeble version of our own magnetosphere, likely incapable of the complex plasma dynamics we see at Earth, or the gas giants. That view has been completely shattered. Thanks to the legacy of NASA's Messenger mission and the recent, daring flybys of the BepiColombo mission, we now know Mercury's magnetosphere is a powerhouse of energy. BepiColombo is actually two spacecraft stacked together, and the hero of our story today is MIO, the Mercury Magnetospheric Orbiter, developed by the Japan Aerospace Exploration Agency. MIO was designed specifically to hunt for these electromagnetic secrets, carrying a state-of-the-art suite called the Plasma Wave Investigation. And it was during the flybys in October 2021 and June 2022 that MIO's instruments came alive. As the spacecraft swept through the dawn sector of Mercury, the region where the planet rotates from night into day, it picked up distinct, powerful electromagnetic emissions. On a visual spectrogram, these appeared as diagonal lines rising in pitch. To a plasma physicist, this signature is unmistakable. It is the signature of Whistler-mode chorus waves. We call them chorus waves because, when converted to audio on Earth, they sound like that dawn chorus of birds I mentioned. Finding them at Mercury was a massive triumph, because it proved that despite its tiny size and lack of atmosphere, Mercury supports the same fundamental plasma physics as Earth and Jupiter. But the Hermean Chorus has a unique dialect, shaped by the planet's eccentric magnetic field and its perilous proximity to the Sun. So let's get into the physics. What exactly is a Whistler-mode wave? To understand this, you have to imagine the microscopic dance of particles. Mercury's magnetic field is filled with plasma, which is a gas of charged particles, primarily electrons and protons from the solar wind. These particles are trapped. They spiral around magnetic field lines, like beads sliding down a twisted wire. As electrons spiral, they gyrate at a specific speed called the cyclotron frequency. Now imagine an electromagnetic wave moving through this plasma. If the wave oscillates at a frequency that matches the gyration of the electrons, a resonance occurs. It is very similar to pushing a child on a swing. If you push at the exact right moment in their arc, you transfer energy to them efficiently. In the magnetosphere, this energy transfer causes the wave to grow in amplitude. This amplification happens in a non-linear way, creating a feedback loop where the wave gets louder and creates a phase bunching of electrons, which drives the wave even harder. This explosive growth allows the wave frequency to drift rapidly upward, creating that characteristic chirp or whistle. But here is the critical question. What makes the electrons unstable enough to generate these waves in the first place? It comes down to a concept called the loss cone. As electrons bounce back and forth between Mercury's magnetic poles, they encounter stronger magnetic fields which act like mirrors, reflecting them back. However, particles that are moving too parallel to the field line don't get reflected. They dive deep into the polar regions and are lost, crashing into the planet's surface. This creates a hole in the electron population. Nature hates this imbalance. The plasma seeks to return to equilibrium by scattering the trapped electrons into this hole, or loss cone. The mechanism it uses to do this is the Whistler-mode wave. The wave grows by eating the energy of the trapped electrons and scattering their direction. It essentially pushes them off the magnetic cliff, sending them raining down onto the planet. This is the heartbeat of the Hermean Chorus, a continuous cycle of trapped solar wind energy being converted into plasma waves and precipitating particles. This is where Mercury gets really interesting compared to Earth. Mercury is not a perfect magnetic dipole. Its magnetic heart is offset. The magnetic equator is shifted northward by about 480 kilometers, which is roughly 20% of the planet's radius. This offset has profound consequences. It creates a lopsided magnetosphere. Because the magnetic center is shifted north, the magnetic field lines in the southern hemisphere are longer and have a different curvature. This creates a larger loss cone in the south. Paradoxically, a larger loss cone creates a stronger instability. It provides more free energy to drive the waves. Simulations and BepiColombo data suggest that the strongest chorus waves are actually generated in the southern hemisphere, driven by this massive anisotropy. However, once these waves are generated, they travel along the field lines. A wave generated in the south travels north. As it travels, it scatters electrons. Because of that offset geometry, the modeling suggests that while the south drives the waves, the north receives the punishment. The precipitation of energetic electrons onto the northern surface is approximately 2.5 times more intense than in the south. The dawn sector of Mercury becomes a chaotic engine of wave activity, a localized storm of electromagnetic energy focused by the planet's distorted heart. Now, you might ask, what happens when these electrons hit the planet? On Earth, when Whistler mode waves scatter electrons, they hit our atmosphere and create the beautiful glowing aurora. Mercury has no atmosphere. It only has a thin exosphere. So the electrons don't stop. They scream down the magnetic field lines at significant fractions of the speed of light and slam directly into the solid rock of the surface. When a high-energy electron hits a rock, specifically atoms like magnesium, silicon, and calcium in the regolith, it knocks electrons out of their orbits, releasing high-energy photons in the form of X-rays. This is known as X-ray fluorescence. It is essentially a surface aurora. If you had X-ray eyes and looked at Mercury's night side, you would see the ground glowing. And this glow isn't steady. It flickers and pulses in time with the chirps of the chorus waves above. Researchers have proposed an electron dewdrop model, where distinct packets of chorus waves cause distinct bundles of electrons to rain down, creating a patchy, flickering X-ray aurora on the ground. This means the song of the magnetosphere is literally etching itself into the surface of the planet, potentially chemically altering the rocks over geological timescales. There is another subtle distinction we need to make regarding the sound. On Earth, we have a plasmasphere, a dense donut of cold plasma that rotates with us. Inside this region, waves usually turn into a steady hiss, like white noise. Mercury is too small and rotates too slowly to hold onto a dense plasmasphere. The solar wind strips it away. This means the waves observed by BepiColombo are predominantly the discrete, structured chorus type. They are naked waves, propagating without being trapped in a dense fog of hiss. However, the data does show some complexity, with narrowband Whistler waves humming near the magnetotail, likely generated by the violent snapping of magnetic field lines on the night side. This discovery allows us to perform a grand experiment in comparative planetology. We can now compare the same physics across 3 scales: the giant magnetosphere of Jupiter, the medium-sized Earth, and the tiny Mercury. The physics holds up beautifully. The frequency of the waves scales with the magnetic field strength. At Jupiter, the field is immense, so the waves are high-pitched. At Earth, they are in the human audio range, from roughly 0.5 to 10 kHz. At Mercury, because the field is weak, only about 300 nanotesla, the whistles are deep, low-frequency groans compared to Earth. But relative to the local environment, they play the same tune. This even helps us understand moons like Ganymede, Jupiter's largest moon, which also has a mini magnetosphere. If strong Whistler waves are accelerating electrons into Ganymede's icy surface, they could be driving chemistry that creates oxygen, potentially influencing the habitability of its subsurface ocean. So, how do we actually hear this? The PWI instrument on MEO uses a search coil magnetometer. It's a coil of copper wire that detects magnetic fluctuations as small as a quadrillionth of a Tesla. Since these are electromagnetic waves, not sound waves, we cannot hear them directly in the vacuum. But because they occur in the audio frequency range, we can feed the signal into a speaker. If you listen to the raw data from the dawn sector, you would hear a low rumble of the solar wind background, punctuated by those distinct rising pew-pew sounds, often clustered in bursts. This sonification is a diagnostic tool for physicists to distinguish between different types of plasma activity. We are currently only in the teaser trailer phase of this mission. BepiColombo has only performed flybys. In late 2025 or early 2026, the spacecraft will enter orbit. MEO will separate and take a highly elliptical path to dive deep into the magnetosphere. We are waiting for the global map. We want to see if the chorus happens at dusk or on the night side. We want to catch the smoking gun, simultaneous measurements of the waves, the precipitating electrons, and the X-ray flare from the surface below. Catching that chain of events is the holy grail. It will help us quantify exactly how much energy is being dumped into the surface, which might explain mysterious features like the hollows and the dark carbon material coating the planet. The image of Mercury has been transformed. It is no longer just a cratered rock. It is a world wrapped in a dynamic, invisible cloak of energy, where magnetic fields snap and reconnect, launching beams of particles that create X-ray auroras on the ground. The Hermean Chorus teaches us that the universe is alive with activity, even in the most inhospitable places. As BepiColombo prepares to enter orbit, we are finally tuning our radios to the full symphony of the innermost planet. The Song of Mercury is playing, and we are finally learning the lyrics. Thanks for listening to G Fun Facts Online.